Good. So thank you so much for the opportunity to talk. And I'm going to tell you about pairwise states versus address states and the geometric phase for monopoles. Now, I don't expect anybody to know what pairwise states or address states are right now, but I hope you'll know what they mean after the talk. So here, I just wanted to draw a little roadmap of why I care about monopole scattering. I think it's a beautiful topic in quantum field theory that has gotten some attention over the years and the decades, but there's still so much to explore in it. And specifically, what you should think about is Dirac monopoles. So I'm not talking about the richness of God monopoles and whatever physics they might have in their core. Just the theory of taking QED and then putting these extra ingredients, these point-like magnetic charges, already vastly enriches the quantum field theory structure of the theory. And it leads to an interplay between topology, which is somehow linked to Dirac quantization and the fact that E, the electric charge of any charge, times G, the magnetic charge of a monopole, has to be a half integer. Quantum field theory, including very surprising effects, like the fact that monopoles, and not just God monopoles, could actually catalyze proton decay with very large rates in a non-decoupling process, which I'll explain further down the line in this talk. This is something that we can show it has to happen by deformed angular momentum selection rules for the charged monopole system. And these are big words that I'll explain more throughout the talk. And the last element here is group theory, because when you have a point-like electric charge and a point-like magnetic charge, and you account for the photons that are exchanged between the two, and even if they're very far away from each other, they can still exchange a very soft photon. That actually deforms the structure of the Hilbert space of the theory. And what we had to do is we had to redefine the Hilbert space and redefine multi-particle states that have to do with monopoles and charges. And that completely changed the definition of the S matrix for the scattering of charges and monopoles. Good. So let me jump right in. And I'll start by reminding you what I mean by a monopole, specifically a Dirac monopole. So again, this is just a point-like magnetic charge. And we know from Maxwell's equations that monopoles are forbidden. So what Dirac taught us in the early 20th century is that you could actually have a monopole solution in electrodynamics, but the price to pay is that there's a Dirac string, which is like a semi-infinite solenoid connected to the monopole. Now, for this to actually be a monopole solution, this Dirac string would have to be a gauge artifact, something that cannot be detectable by any experiment. But of course, we know that in the quantum theory, we can do a Hartog-Bohm experiment to pick up magnetic fluxes. So if we take an electric charge and take it in a loop around the Dirac string, we better not have any observable that allows us to know whether the loop that we did went around the Dirac string or not. And that's only possible if the Hartog-Bohm phase incurred by a particle going in the loop has to be an integer times 2 pi, which leads to Dirac quantization. This is the famous argument for Dirac quantization. And of course, there are more fancy ways to see Dirac quantization. For example, in a gauge bundle definition of the monopole, in which you see that the correct topological definition of monopole charge is first Chern number. And I can explain more later if people are interested. Now here comes the punchline. Why the system is completely different from anything else. And this is a calculation that J.J. Thomson did already in 1904. Let's take a point-like electric charge and a point-like magnetic charge, and they're completely static. We will see that the system actually has angular momentum, which is non-zero, even though these two particles are completely static. And this could be calculated through just a Jackson-type calculation. We take the pointing vector and we cross it with R, and we integrate over all of space. I'll spare you the math, but the result is quite surprising. It's minus E, the electric charge of the charge, times G, the magnetic charge of the monopoles, times R hat. So this is just the direction between the monopole and the charge. But this is distance independent. So I can throw the monopole to like Andromeda, and yet there'll still be, because I'm integrating over all space, time, an irreducible angular momentum associated with the field. And we know from our first semester of classical mechanics that when we solve some kind of scattering problem, we need to conserve angular momentum and energy. So this will deform scattering experiments completely, and will also have meaning on the quantum side. Any question about this? Good. So let me draw you a picture of what this does for classical scattering. Let's say I have a heavy monopole sitting here, and I take an electric charge here and I just throw it on the monopole. If this were not a monopole but an electric charge, the charge would undergo Keplerian motion in the plane, like this. So let's draw it on the side here. So just do this. On the other hand, because of this extra angular momentum, I can write that the J total of the problem is R cross T minus EG times R hat. This is the extra angular momentum in the problem. And when I dot this with R hat, I find that this is minus times U. Which means that if this is the total J of the system, there will be a cone around this J with a fixed angle dictated by EG over J total. And the charge would have to move along this cone. So we would be able to do all kinds of rotations here and would have to leave on that cone. So this is very different from here. And this is a long range effect because the charge could go very far away, but it keeps feeling the electromagnetic field from the monopole, keeps exchanging soft photons with it. So it completely deforms the long range behavior of this. Moreover, already you can see that this is a non-decoupling effect. Because let's say I took this charge and I threw it really hard to the point that it passes very close to the monopole core. So let's zoom in, and let's say that this is the monopole core. I don't know anything about the UV physics. It could be God, string theory, you name it. All I know is whatever the physics is here, it won't lead to the charge leaving in this direction, because this is forbidden by the angular momentum selection rule. So there's a non-UVIR decoupling here. Whatever the UV physics does, it has to make the charge leave on that cone. And this theme of UVIR non-decoupling will be kind of recurring in the work that I will show. Questions? Good. All right. So these are kind of overarching questions of the line of research that we did. This is a group of friends and collaborators, especially Chava, who's sitting here, John Turning, and many others. And what we asked specifically is, what is the space of quantum multiparticle states that involve charges and monopoles? Following historic work by Zwanziger, that was a great reference for our work. And in particular, these sub-questions appeared here. Where does the extra angular momentum enter in the quantum field theory? The one that we saw that performs classical scattering over there. Also, what is the role of Dirac quantization? And finally, what is the role of the Dirac string in the quantum field theory?
So try to understand. Sorry. No, go. Just try to understand again this argument of IRUV. I mean, this is just a conservation law, no? I mean, what's the difference between this just angular conservation, which you preserve and you say, in the end, if I look back, angular momentum is just conserved, or energy conservation? I can take a particle, I can kick it in to some very strong, to look into the proton. I don't care what it's made of. In the end, I know that there's energy conservation coming out.
Yeah.
So what's the difference?
So here there's angular momentum.
The mixing in some sense.
Because the angular momentum generator, and let's say I quantized the charges in the background of a heavy monopole that sets the background field. the J operator at the quantum level has, it's the J that commutes with Hamiltonian that has the monopole background field in it. So there's a contribution to the angular momentum from the field. And that you don't have anywhere else. But this will be, there will be an even better answer, which is the bulk of this talk, which I'll tell you, I'll give away the message already. This is the angular momentum associated with the soft photons, or the soft photon dressing of the monopoles and the charges. And that's what you have to take into account, and that's what deforms your Hilbert space. So it's just take charges and monopoles, add anything that has to do with soft photons, and then you have it. Good. All right, so, and that leads me directly to this slide, which is, as soon as we have angular momentum, which is not an orbital angular momentum associated with the charge or the monopole, it's somehow up in the air. I already told you it's associated with soft photons, but let's not go there yet. That means that my multi-particle states cannot be just tensor products of single particle states. If they were, I would act with a J operator here. I would pick up the sum of the J, the single particle J of the charge, and the single particle J of the monopole, and I would miss out on this key ingredient, the angular momentum associated with the electromagnetic field. So we already know that we have to construct multi-particle representations which are completely different from what you find when you open like chapter 2 of Weinberg, for example. They're not tensor products of single particle states. In other words, they don't form a Fock space. And the correct answer is that it's not a Fock space, it's just the product of single particle states times the coherent state of photons, which is like, has an indefinite number of particles. Good. So we have to redefine what we mean by multi-particle states of charges and monopoles, and this we did in a paper already 2 years ago. And what we realized is the following. When I write down a multi-particle states, these are the momenta of the different particles, and these are the spin/helicities of the problem. There are extra quantum numbers here, which we call pairwise helicities. They are supposed to reflect the extra angular momentum in the electromagnetic field. And these QAJs are just the generalizations of this E times G. So we write EI times GJ minus EJGI just because generically a particle could be a dyne and could have both an electric and a magnetic charge. And this correct combination is what's quantized by Dirac-Schwenger quantization. So it's quantized from very different reasons. It's quantized by Dirac quantization, this trick with the string and the heart of Bohm experiment. It's quantized by topology. But here we are showing you that it's also quantized by group theory, because in the multi-particle states, it plays the role of a helicity. And we know that helicities are in labels of representations of a U1, and they come in half integers. So this is, again, this marriage of topology and group theory, and the Q of T will follow suit. The way these multi-particle states transform under a unitary representation of the Lorentz group is that the momenta are just Lorentz transformed. There are factors associated with the single particle rotation. And then there's this extra ingredient. There's this overall pairwise phase, which is the sum over the helicity associated with every pair of particles in the multi-particle state, times a little group phase, which we know how to calculate, and I'll show you in the next slide how to do so, which depends on the momenta of every pair of particles and the Lorentz transformation that I'm doing. So that's the key thing here. And when I take the derivative of that phase, I will get this extra angular momentum in the problem. Questions about this? Good. So let's dive a little more into how to calculate this phase. And I will do it not just to tire you out, but I will do it because later we will show the quantum field theoretic source of this phase. We'll show how to calculate it from soft photons. So it's good to go over the details of how it's derived in group theory. So I have a multi-particle state with many different particles. For each pair of particles, I go momentarily to its center of mass frame with the two momenta aligned along the z-axis here. And now I ask myself, what is the subgroup of Lorentz transformation that leaves these two momenta back to back along the z intact? After thinking about it for a few minutes, you'll see that it's just rotations about the common axis. So this is a U1. Note already that these can be massive particles. Usually we think of the little group of massive particles as absolute free rotations in the center of mass of the single particle. But once you have two and you have to stabilize two momenta, these are just U1 rotations. So that already explains why there are helicities associated with pairs of potentially massive particles. And as we know, we can represent U1 rotations by these half-integer labels, just like electric charges. And these are the ones that will turn out to be the Dirac quantized pairwise helicity, and they're associated with pairs of particles. Now we can do the usual Wigner trick. We can define a canonical Lorentz transformation that takes us back and forth from the center of mass momenta to any other frame using this canonical Lorentz transformation. And it's easy to show that in this case, the way Lorentz transformations are represented in this generic P1, P2 state is by a transformation that involves the pairwise little group phase here, which is defined in this manner. This is called Wigner's trick of induced representations. Specifically, there's freedom in choosing the Lorentz transformation. There's U1 rotation freedom in fixing this canonical Lorentz transformation that takes us from the center of mass frame to the finite momentum frame. And we fix this rotation by demanding that this entry of the canonical Lorentz transformation will be orthogonal to some generic direction n. And this is the definition of this epsilon. It's just the Levi-Civita contraction of three vectors. So this is just the convention. I have a rotation freedom, and I'm saying be orthogonal to this direction. It's an easy computation to show that then the little group phase is uniquely defined as basically an angle between two normals in 4D. It's also called a dihedral angle because it's like the angle between two hyperplanes in 4 dimensions. And this is the answer for the little group. Now introduce a random direction, but this direction is actually morally like the Dirac string, which enters into our construction in this way. Questions about that? Good. All right. So what did we do once we defined these states? We know that the S matrix for the scattering of particles is just the dot product of an in multiparticle state and an out multiparticle state. And because of these extra angular momentum characteristics of these multiparticle states, we're able to derive angular momentum selection rules on the electric magnetic S matrix that are very different from any S matrix that involves non-magnetically charged particles. Specifically, we derived all 3-point amplitudes that involve charges, monopoles, and diodes. We reproduced the forced chirality flip in Lowe's partial wave for fermion monopole scattering. This is the surprising fact that if I have a monopole here and I have an S-wave left-handed fermion coming in, what comes out has to be a right-handed fermion 100% of the time in the S-wave. Usually when I have scattering, let's say I shoot a proton on something, most of the odds is that the proton is going to stay a proton. In this surprising process, if I'm in the S-wave and I start with a left-handed fermion, it's not allowed to stay what it was before the scattering. It has to undergo chirality flip as demanded by our modified selection rules. So we were able to derive this effect. We also reconstructed monopole spherical harmonics from contracting together spinor helicity variables that transform under this extra angular momentum, and did many other things that you can see here. And the last thing I want to point out is that the gut version of this process is monopole catalysis of proton decay. It's the fact that I throw in a proton, and this is an SU5 gut monopole. What comes out has to be an electron and a pion. And this is, again, a process which is not suppressed by the mass of the monopole. It's a non-decoupling process, and it saturates the S-wave unitarity bound. This is a huge process, and it's the dominant bound on the existence of magnetic monopoles in the universe by, say, 10 orders of magnitude. So this is a big thing. Okay, and after this very long half the talk introduction, let me get to the actual point of the paper that we just put up recently. We had this fancy group theory definition of the multi-particle states, but we always thought that the physics should be somehow related to the fact that the monopoles and the charges exchange soft photons between them. And somehow we thought there should be a way to avoid all this confusing group theory and just kind of do something more mundane. Just, shut up and calculate the soft photons exchanged between monopoles and charges, and derive in this way the extra selection rules and the extra phase associated with monopoles and charges. And indeed, our intuition was correct. We've discovered that these pairwise states that we derived using this pairwise group theory are exactly just multi-particle states of charges and monopoles when they are addressed by all soft photon lines, the ones exchanged between them and the ones radiated to infinity. And these photons exactly reproduce the pairwise characteristics of these multi-particle states. So let me remind you what I mean by addressed states. Essentially, you might remember from quantum mechanics that we could have the Schrodinger picture where all the time dependence is in the quantum states and the operators are time independent, or the Heisenberg picture where the states are fixed and the time dependence in the operators. And then we have the interaction picture in which we kind of rotate just the H naught into the time dependence of the quantum states. This is similar here. I identify a part of the interaction between the charges and the monopoles which gives me trouble, which gives me IR divergences. And that's just the Coulomb part of the interaction that gives me a Coulomb law, that gives me IR divergences. And what I do, I rotate this part of the potential. The T goes to plus minus infinity means that I take the infinitely soft, zero energy photons exchanged between different charges and monopoles in my case. And I rotate it into the definition of the asymptotic states of the S matrix. So now it's not in the Hamiltonian then, or the interaction term then, calculating expectation values of. It's part of the definition of the asymptotic states. And this is what dressing really is. How do I do this? I define my dress states, which now have two cats here, to be the usual quantum states, acted on by this operator. It's the operator that basically dresses the outgoing states with all possible soft photons. And now when I calculate the S matrix between an in and out state that are defined this way, it's going to be manifestly finite, and that's the conventional solution to the QED IR problem. What we did is we did this dressing not just for charges, but for charges and monopoles as well. We can do a little bit of math, and we can trade this time-ordered exponential, sorry, the t should be outside here, into two factors, e to the phi fk, which is morally speaking just the integral over all soft photons exchanged between two external legs of the S matrix, and e to the r, which is basically the generation of the retarded field that's created by the outgoing charges moving along a straight line into infinity. So the combination of these two factors gives me exactly the dress states, which give me a finite S matrix. Questions about this? And now we want to do it for charges and monopoles. So what I do is I essentially just dualize. Instead of just having the electric current density coupled to a photon, I also have the magnetic current density coupled to a dual photon. So this A tilde should be a B. That's just the typo, but morally speaking, this is what this B is. It's an A tilde. And note here a very important point that is crucial. There are two photons. It's not like a U1 cross U1 situation. There's just one U1, there's just one photon. And you can see this by the fact that these two fields in their mode decomposition have exactly the same creation and annihilation operators. So they differ to each other from each other just by their polarization vectors, which are, morally speaking, the dual of one another. So that's a very important point. Both the charge and the monopole couple to the same photon, but the coupling is just different because of the tildes here in the expansion of the magnetic presentation of the same photon. Okay, good. So what do we want to show? We want to show that these Druss states, which, let me remind you how they're defined. They're the normal quantum states acted on by this Drussing factor that drusses them with all possible soft photons. We want to show that their Lorentz transformation properties are identical to the ones of the pairwise states that we defined from group theory. And specifically, you can take an infinitesimal Lorentz transformation and write its unitary representation as follows, using the Noether generator mu nu for Lorentz transformation. This is a theory-specific operator, right? Different actions have different Lorentz generators, Noether generators for Lorentz transformations associated with them. This is specifically the Noether generator in QEMD. So just a bunch of fields in their creation and annihilation operators. And we want to show that when we act with this on the Druss states, with this real photon and virtual photon factor, we get exactly this extra pairwise phase. We can do a little math and use the Baker-Campbell-Hausner formula and arrive at this this will be one of the more complicated equations here. So basically we want to show that an infinitesimal pairwise low group phase is generated by two factors. It's generated by how Lorentz transformations act on the real soft photons, or more specifically on the retarded electromagnetic field sourced by the monopoles and the charges, plus the shift of this extra virtual soft photon. These are the photons that are exchanged between lines of monopoles and charges. And we just prove this by explicit computation. Any questions? So when do I need to finish?
At most, including questions quarter to.
Okay.
Into it.
Sure. Great. So what do I need to do? I just need to calculate. This is another generator that is defined in my theory. This factor is defined. I just need to canonically commute these elements. This will essentially be like a loop integral of just summing up the entire, it's like an iconal. It's the entire ladder of soft photons exchanged between legs. And this is something that I already know. So I want to just prove that this equals to this. So we'll start by calculating this part. The shift of the soft photon phase under a Lorentz transformation. So what is this soft photon phase? It comes from the commutator of the 3-point vertex of a charge or a monopole emitting a photon. And the commutator of this potential at two different times. Let me isolate the key ingredients here. There's an electric coupling to the photon that comes with the usual polarization vector. And there's a magnetic coupling to the dual photon that comes with the dual polarization vector. Now, if you look at it and you perform the sum over these two things, you see that this looks like very familiar for anybody who's worked with monopoles before. Propagator that involves the two momenta of the external legs, the Dirac string, and the momentum of the photon. Here. Note that there's a 3D analog of such a propagator, and that's the propagator, the Chern-Simons propagator in 3D. And it's not a coincidence, because there's something topological in this theory. The exchange of a Chern-Simons propagator in 3D allows us to compute topological numbers. It allows us to compute the linking number of two curves. This one and this one in 3D has linking number 1. And I can calculate it by just taking a Chern-Simons propagator and sliding it over the two loops and calculating the expectation value of these two Wilson lines. A similar thing will happen here with this propagator. But that's a side note that if you're interested, I can talk about later separately. Okay. So, to calculate the soft photon phase, this ladder of exchange, I need to essentially do a Feynman integral with a propagator like this. And if I kind of present it more explicitly, what I have is a sum over all the different pairs that I have in my multiparticle state. A prefactor, which is just the couplings. These are exactly the pairwise velocities, whatever is Dirac quantized. I have an integral which just picks up the different momenta of the particles involved in my theory. This is the definition of this factor. It just means that if I have several momenta going in different directions, I keep picking up this one and then calculating the integral between the two of them. And finally, I have this integral, which is basically the imaginary part of the Feynman integral symmetrized over the different directions in the problem. And this is the Feynman integral. It has this epsilon upstairs. It comes from this Chern-Simons-like propagator. I have a k squared here, and I have basically the two momenta P1 and P2 of the two particles I picked. And P3 is just another name for the Dirac string. So it's not another particle, it's just the Dirac string here. So all that remains is to calculate this Feynman integral, but alas, it's 0 over 0. And let me explain to you very simply why it's 0 over 0. From Lorentz invariance, the result of this integral with the k here will be either proportional to P1 or to P2 or to P3, but I'm contracting it with an epsilon. So if I put a linear combination of P1, P2, and P3 here, I'm just going to get 0. But I'm also getting a 0 from the integral over the denominator, just by dimensional analysis. So this is 0 over 0. It needs to be regulated. And for several months, I've kind of banged my head against this integral and didn't really know what to do. Until Xu Dong, who's a student in the Beijing group who's been in Cornell for a year now, working with Chaba, came up with simply a brilliant idea that saved us. And this idea was that we actually don't need to calculate this integral, because all we care about is not the absolute value of this phase. We want to know what the delta of this phase is under a Lorentz transformation, because we want to know the Lorentz transformation properties of this quantum state. And surprisingly, while the I is ill-defined, the delta I is completely well-defined. And the reason is because there's now an extra direction in the problem. There's the direction of the Dirac string before and after the Lorentz transformation. So then you get an epsilon that exactly has 4 different directions, and it's non-zero. And he showed through, in position space, through Stokes' theorem, that the result of this integral is nothing but the solid angle between the 4 different directions. The P1, the P2, the Dirac string before the Lorentz transformation, and the Dirac string after the Lorentz transformation. So this is already quite beautiful geometric interpretation of this integral. And maybe I should have had an extra bullet here of geometry, because suddenly we have a solid angle in the problem. When you do this symmetrization over different directions, you get a dihedral angle. The 4D solid angles reduced to 3D solid angles, and then to 2D angles, which are basically the direction between, the angle between two directions and essentially projections into 2D of the different directions of the problem. And lo and behold, this has no right to be exactly equal to the phase -2, the phase that we got from the group theory, but somehow the stars align and we get exactly -2 this result. So we're almost there. So what about the contribution from the real photons? We need to show that this equals to this infinitesimal little group phase, this is 2, this should be a -1 of the little group phase. And in 2 slides, you'll see that that's indeed the case. So what we need to do is to calculate the structure. So we need to say what the generator of Lorentz transformation is in our theory and calculate this commutator. And the way you do it is pretty standard. You write the energy momentum tensor in your theory, which is associated with a kinetic term for the 2 versions of the photon, the F and the F dual, and also the part that comes from covariantly coupling to the matter fields in my theory. This is just the covariant derivative part. And now the generator for Lorentz transformations is just the anti-symmetrization of the x-coordinate with the energy momentum tensor. So this is the standard definition of the generator of Lorentz transformation. Now commutators with this operator that creates a soft photon cloud are equivalent to taking this formula and whenever you have a field, substituting the linear vector, the retarded field generated by the outgoing charge and monopole in this theory. So we just substitute the retarded field, and I'll save you the details. But what we find is that if we sum the contribution from the covariant derivative from the kinetic term, we get exactly minus this phase. So we proved by explicit commutation that the group theory defined pairwise states are identical to the soft photon dress states of QEMD, quantum electromagnetic dynamics. Good. So this was a little bit of a bumpy ride, but I want to reward you with a cool bonus. Okay? I'm going to show you that these multi-particle states have a geometric or a Berry phase associated with them, which is something you usually see in condensed matter, and you hardly think about it in the context of quantum field theory. And we'll see what that geometric phase gives us. What happens when I do a 2-pi rotation? I need to look at the little group phase associated with the Lorentz transformation, which is just a 2-pi rotation. And by explicit computation, we can show that it's plus minus 2-pi times the sum of all the pairwise helicities in the problem. Now let's say we only allow this phase to be either 0 or pi. Okay, we don't want any fractional statistics or violation of the spin statistics theorem in our quantum states. That immediately tells us this sum over pairwise helicities has to be an integer over 2. So this is a completely quantum field theoretic derivation of Dirac quantization without talking about Aharonov-Bohm experiments and flux tubes and all these things. It's just from the quantum field theoretical definition of the state and demanding that the statistics is either bosonic or fermionic. And this is the geometric phase associated with our system, because that's the phase that your quantum state gets after you do a full circle rotation. The bonus here is if the sum of all pairwise helicities in the system is half integer, this phase actually ends up being a pi. So we get an extra minus sign. So what did we do here? We took a system that's made out of bosons, a boson monopole, a boson charge, and a cloud of coherent photons, and as we know, photons are bosons as well. And this entire system together behaves like a fermion, because the coherent state of photons actually has fermionic statistics when it's sourced by monopoles and charges with sigma q equals half. So this was known in the past, even Tuft wrote about it, but it wasn't shown in QFT. It was only shown when you quantize a charge in the presence of a heavy background monopole. And we show this from the very definition of the multi-particle Hilbert space, that you can actually make fermions out of bosons. And everything goes along for the ride. These will have Pauli exclusion principle, exchange statistics, all of that has to come follow through if the spin statistics theorem is going to be obeyed. Questions about that? Okay, so let me conclude. Multiparticle quantum states for charges and monopoles are not in Fock space. They have pairwise helicities, these extra quantum numbers associated with pairs, and pairwise little group phases. The pairwise little group provides modified angular momentum selection rules, constraining scattering and leading to very surprising processes, like a left-handed fermion becoming a right-handed fermion with 100% of the S wave, or even a proton becoming an electron and a pion 100% of the time in the S wave. But what we also showed here is that this is not really, magic and mysticism. It's just when you meticulously account for the effect of the soft photons exchanged between monopoles and charges, you get all these surprising effects, including the modified angular momentum selection rules. The pairwise little group phase is the shift of the soft photon phase, and also a contribution from the real photons under a Lorentz transformation. And finally, when you account for the soft photons, it shows you can actually make fermions out of bosons. That's it.
Yeah, very good. Other questions?
Have you thought at all about how, for instance, like the modified angular momentum selection rules would like maybe change or muck up anything for like models where you produce monopoles in the early universe? Or
Yeah, I mean, I was talking to Shuik a little bit about it. If we can look in the C and D for these things,
that's what I'm.
Especially because it seems like there's an integer here, and if you can measure something that has to be an integer, that could be a really nice smoking gun. We never reached anything concrete, but I think it's mostly because we were busy, so it's worth thinking about.
So the presence of monopoles somewhere would alter the scattering of just the charges. Because because you always have these soft photons around that you don't know you do, but then can you kind of design an experiment to search for monopoles which only full scattering of charges?
Well, it's hard because the effect you can see it classically. Well, I erased it, but there was classically there was a cone, right? So whatever was a plane became scattering on the cone. But the opening angle of this, or the converse of the opening angle of the cone, goes like Eg over the total J. Now, if your leg to Andromeda is very long, then the cone is actually becomes almost like a plane.
Yeah.
Which I'm not sad about, because if it were anything different, then I would have thought it was crazy, because it violates locality. And so I wish.
Yeah.
Can you have interesting effect in non-relativistic processes, if this particle and the monopoles goes very slow?
Yeah.
I was just thinking that that somehow the electrodynamics that we see in the non-relativistic limit is very much affected by the fact that we don't have magnetic charges. For instance, we have formation of bound state just by dipole operators. I mean, all the structure is very tight. So I don't know if it has been studied. How this gets modified. Say there would be a potential, no?
There would be,
let's say if you want the ladder diagrams that you're summing the conal approximation in the non-relativistic approximation, in the other limit, it just give you an effective non-relativistic potential.
You're just moving in a direct potential of the model. Yeah, it's true. It modifies your spherical harmonics to monopole spherical harmonics. It makes your classical limit to be motion on the cone. And we actually...
So the trajectories, the classical trajectories of this problem, what are? Did you study this?
They're just motion on a cone. And I have a different paper in which I took the classical limit of scattering of the charge on a monopole, but also the gravitational analog. So there's Taub-NUT space, which is essentially like the gravitational version of the monopole. Yeah. And what I did, I wrote down the quantum amplitudes using this method, took their classical limit, and what I got is geodesics in this Staubnut space. And the geodesics were really motion on the cone, just like here, because the angular momentum is deformed in the same way by the long-range interaction. But I'd be very happy to talk about more ideas in that context. I think there's much more to do.
But yeah, I was just thinking that you could get like the analogous of what do you say? Essentially positronium. Like if you go in the very non-relativistic limit of this, or maybe it's not true. If I have like a monopole, and then I have some electric charge, and
well, you won't have bound states, but if it's a diene rather than monopole, then you
they can't bound. No, no.
I mean, if it's a diene, they're bound by their mutual and purely
so
electric.
how do I produce a pair? Just the Redian. If I was just thinking how do I produce like a pair of monopoles? It's just the Redian.
Yeah, I do.
Or like
plus and
fusion,
minus, and
I see. No, you need something that is charged under both. I see.
I have one more question. I think maybe I bumped you about this once, but I don't remember. Is this formalism compatible with super symmetry?
So I have a draft in the drawer.
Okay. So yes.
Yes. I talked to Seth about it.
Silly question here. So how much goes through of this story when you Higgs the differentiate the photon?
I think nothing suffices because this is a deformation of the asymptotic Hilbert space, and if the photon is only finite range, then you're basically. But I mean, let me put it
within the range.
Yeah. So if you could essentially define a near zone and a far zone, and in the near zone, you're pretending that the photon is massless and the Hilbert space is deformed, and you'll have this like deformed selection rules and stuff. And then outside, you're supposed to go back to the undeformed case.
The other option that I'm thinking naively about is that the Dirac string can be actually produced by a vortex. So.
Yeah, so the Dirac string ends up being just a flux tube between a monopole and an anti-monopole. And when you fix the theory. Because that's like confining the monopole.
Okay. So I think we can thank Ofri again.